Morning, everyone. Welcome to this session, doctoral meeting session on our space science and technology PhD program. I would like to thank you all, our 7 speakers today, and all the audience, including the supervisors, for being here. Today, we're going to be discussing, talking, and listening to the presentation of the PhD students that are working on different problems related to astrodynamics, space tethers, also space debris, GNC problems related to space, etc. Right, so it's quite interesting topic. We have also some industrial PhD thesis, some academic PhD thesis, and I hope you all enjoy. Okay, so sorry for these minutes of delay and these problems with the connections, but I think we are all here now. We're gonna start with Luca and Sadaf. They're gonna be presenting topics on space tethers, right? And then we will continue with Sergio and with the other established before. Okay, so whenever you are ready, Luca, please go ahead.
Okay, so thank you very much, Manuel, for your introduction. So my name is Luca Chiabó, and today I will present my thesis regarding emissive long-wave probes with applications to lower function electrodynamic tethers. This is that I'm carrying out here under the supervision of Professor Sanchez Arriaga. After a brief introduction of the topic, I will speak about the methodology that we are following, and then I will present some of the results that have been gathered so far before eventually summarizing the main contributions and the work plan for the next future. So let us start now by having a look at what lower function tethers are. Basically, these are devices that have been proposed as promising deorbiting technology. As you can see from the video that I'm showing to you, tethers basically consist in long conductors that are deployed from a spacecraft at the end of its mission, and their working principle is quite simple. On the one end of the tether, we have the conductor uninsulated or bare, and this starts collecting electrons from the surrounding plasma. Such electrons are then emitted back at the other end of the tether, thanks to a lower function coating that allow for emission through photoelectric and thermionic effect. These devices, well, thanks to this good electrical contact, let's say a current starts flowing along the tether, and due to the presence of the magnetic field, this in the end results in a magnetic drag that can be exploited in order to deorbit the spacecraft towards the Earth. Of course, the performances of this device highly depends on the current distribution that we are able to generate along the tether, and an estimation of this requires for the plasma tether interaction modeling. This is done taking advantage of the fact that the tether length is much bigger than the dimensions of its cross-section. We can basically see each cross-section of the tether as working as a two-dimensional probe at a certain bias with respect to the surrounding plasma. Therefore, current distribution along the tether would be approximated basically by the current voltage characteristic of a probe that has the same cross-section as the one of the tether. Here on the right, you can see a sketch of the configuration that we are dealing with. In particular, you can see that right now I'm considering elliptical configurations. This is because ellipses represent a good link between the two limit cases of a round tether and a tape tether. This latter geometry having proved to be favorable for tether application because it allows for higher performances, and it is more robust against impact with the small debris, and also it allows for a better scalability of the device. So in the end, the goal of my thesis is to deeply characterize the interaction between emissive probes with such geometry and the plasma configuration that was overlooked in previous works on on emissive probes. Besides lower function tethers, other applications of this work may be linked with dusty plasmas, but also with spacecraft charging. So regarding the methodology, the analysis is carried out with numerical simulation. Here you have the kinetic model that we are considering. Regarding the assumption, we are now working with stationary conditions. We have a probe that is immersed at rest in an magnetized conditioned plasma made out of Maxwellian electrons and singly charged ions. The probe itself is emitting according to a half Maxwellian distribution function, and we are neglecting the population of trapped particles. Based on this set of hypotheses, our problem is governed by the Blaise-Poisson system of equations, and a solution of this system is uniquely identified by these 6 non-dimensional parameters, among which we see there is the probe geometry, its bias, the temperature of the species, and also the emission level beta. A solution to this system is found through a numerical algorithm, a code that goes by the name of FONXG, that was developed from scratch. Basically, this code implements the iterative strategy that is here depicted schematically. What we do is that we iterate over an initial gas density vector until that has been updated self-consistently until it complies with a certain tolerance selected by the user. This code was verified against previous software developed by Chen and Sanchez-Arriaga a few years back for investigating cylindrical emissive probes. And it is mainly made of 2 blocks. The first one is the Poisson solver, which computes the electrostatic potential, receiving as input the density at the nodes of the mesh. And then the Vlasov solver, which on the other hand computes the density consistent with a certain electrostatic potential. In particular, this Vlasov solver is based on what we refer to as a backward-Liouville scheme, which guarantees that the code is free of statistical noise. The Vlasov solver basically works like this. It takes advantage of the fact that for a collisionless plasma, the distribution function is conserved along the characteristic of the Vlasov equation, which also coincides with the orbits of the particles that are written here. And so the distribution function can basically be inferred through a backward integration of such characteristics. How this procedure works? Well, basically, what we do is that for each node of the mesh, we define a second mesh, the energy directional domain, which basically represents our velocity space. So we have a 4-dimensional space mesh in a phase space. A point in this mesh, together with the position of the node of interest, correspond to a set of initial conditions for our orbital integrator. Performing the integration of the characteristics, we are able to identify whether this set of initial conditions yields a trajectory connecting with the outer boundary of the simulation or connecting with the probe boundary, or trapped inside the sheath of the probe. Based on which this situation occurs, we assign the value of the distribution function according to the boundary condition that we are imposing. For instance, for plasma ions, we will have that a finite value will be assigned to the distribution function at this point of the phase space if the trajectory connects with the outer plasma, while the distribution function will be set to 0 otherwise. Repeating this, for the all velocity space, we find this map that I present here for all 3 species that we are considering. And once we have this map, we can integrate onto the energy directional domain in order to obtain the density at the node of interest. Now, let us see some of the results that we have gathered so far. First of all, we have investigated some interesting physical features that arise when we consider elliptical configuration. In fact, when the eccentricity is bigger than 0, basically the system of the characteristic equation presents only one conserved quantity, which is the total energy, and therefore a mixing of chaotic regular orbits can appear, and as a consequence the distribution function is filamented in the velocity space. As you can see here in the image on the right, the boundaries, what this function presents fine structures, has the boundaries that separate, say, points in the distribution function corresponding to different type of trajectories present somehow fractal structure. This is an aspect that has to be taken into account when dealing with the numerical simulation, because it may pose some convergence issues. Besides that, we are also investigating the operational regimes of elliptical probes. In particular, here I would like to talk about the transition into the space-charge limited regime, which is a condition in which, following the increase in the population of emitted electrons in the proximity of the probe, we have a reversal of the electric field there, and therefore some of the emitted electrons, instead of being driven away by the electric field, are actually reflected back to the probe. This is something that is detrimental for lower function tethers application, and in order to measure the impact of this condition on the elliptic probe that you can see here in the inset, what I have done was to select for a fixed, to increase the emission level gradually for a fixed probe bias, and then to plot the ratio between the emitted electrons that actually are capable of overcoming this potential dip with respect to the total emitted electrons of the probe. As you can see, for low values of the emission level, this ratio is equal to 1, but downward a certain threshold value, this ratio starts decreasing in this parabolic-like trend. It is also interesting to compare the results that we obtain for an elliptical probe with the analogous results obtained for two cylindrical emissive probes with radius equal to the semi-minor and semi-major axis of the ellipse. And as you can see from these preliminary results that we have obtained, elliptical probes seems to resemble the behavior of round probes with radius equal to the semi-major axis when it comes to operating in under space-charge limited conditions. Now to conclude, well, these and other results have been included into two papers. The first one was actually recently published in the Journal of Computational Physics, and the second one is currently being prepared and will soon be submitted. Besides that, intermediate results were also presented at three different conferences, and in addition, we have started the procedure to register the software. This is done under the framework of the ETPAC project, which is a project at NH 2030 FET Open project funded by the European Commission, whose aim is basically to develop the orbit kit based on the lower function tether technology. And in this project, we as a research group at the UC3M are involved both as with coordinating tasks and also investigations tasks. Besides that, I am also involved in a smaller project that goes by the name of BBOM, which is somehow complementary to ETPAC because it is aimed at basically addressing the commercial cases of interest for the orbit kit that we are developing in ETPAC. Last, just to quickly conclude, the next activities related with my research will be that of relaxing some of the hypotheses of the model, mainly to extend the code to non-stationary conditions. Besides that, it would be also great to verify the code against experimental results. Let's see if there will be time for this. And I'm also planning to perform a research visit at the beginning of next year, according, of course, to the evolution of the COVID-19 pandemic. Sorry. So this was all from my side. Thank you very much for the attention. And in case you have any questions, I'd be glad to try and answer you.